It's
Okay.
okay.
Okay. And then Olga is a professor at Bauman Moscow State Technical University, right? Okay. So today she's gonna give us some knowledge about the vector databases. Okay. So you're gonna open up the afternoon for us, Olga. What time is it in Moscow?
It's 9 o'clock in the morning.
Morning. All right. Good morning. We are
Good morning.
just finished lunch today, this afternoon. Okay, Olga, it's your stage. Take it away. Thank you.
Thank you very much. My name is Olga, and today I'll tell you about vector databases. I'm not a professor. I'm a lecturer, but very excuse. Thank you. And my courses are programming, C++, databases, and the main course is optimizing machine learning databases. Database optimization is a really huge theme, but if we take the aspect of machine learning, we are talking about data cleaning, searching for target features, applying rules. All mechanisms are aimed at reducing the amount of data, identifying the relevant information for further training of the neural network. Of course, there are many types of databases. Each of them has advantages and disadvantages. Many of them solve specific narrowly focused tasks, serve niche markets, but relational models, relational databases are still very popular. SQL incorporated the best query language ideas to expand its support for modern applications and remain relevant. So many developers are using relational databases with different types of extensions. Of course, in our course, we are studying relational databases. They are more visual, reliable, and intuitive, but traditional scalar databases cannot handle the complexity and the scale of storing text, images, audio, video. Vector databases have been developed for processing these types of data. They offer a new paradigm for data storage and retrieval, specially designed for handle data points represented as vectors in a multidimensional space. Thus, we have added the study of vector databases to our course. Vector databases are used in numerous domains and situations in analytical and generative artificial intelligence, including natural language processing, video and image recognition, recommendation systems, search, and so on. For example, you can use a vector database to identify similar images, documents, and songs based on their content, themes, tonality, and styles. Identify similar ones product based on their characteristics, attributes, and user groups, and much more. In addition to these typical use cases for vector databases, vector database is also the ideal solution for large language models, caching at the production environment level due to its low latency, high scalability, and high availability. It's especially popular to use vector databases to provide search argument generation, which uses large language models and user-defined data or domain-specific information. Vector databases store embeddings or vectors This is a compressed representation of some unstructured object. For example, text, image, or text and image. The vector absorbs the semantic of the object. Using vector databases, you can search for similar objects using special indexes. Embeddings are usually built using large language models. Other words, embeddings are low-dimensional, learned continuous vector representations of discrete variables. Neural network embeddings are useful because they can reduce the dimensionality of categorical variables and meaningfully represent categories in the transformed space. Oops. Sorry. If you try to search the information of how does a vector databases work, you definitely find some kind of this picture. By the way, I've added links to all pictures in presentations, so you can click here and go to the source. So we have unstructured data. They flows through an embedding model, and then they proceed into vector embeddings and stored in databases. But how does embedding model work? And there is one hot encoding. One hot encoding categorical variables is actually a simple embedding where each category is mapped to a different vector. This process takes discrete entities and maps each observation to a vector of 0 and 1, signaling the specific category. The one hot encoding technique has two main drawbacks. First, for high cardinality variables, those who have many unique categories, the dimensionality of transformed vector becomes unmanageable. The mapping is completely uninformed. Similar categories are not placed closer to each other in embedding space. The first problem is well understood. For each additional category, we have to add another number to the one hot encoded vector. If we have million books, then representing these books requires million vector for each book, which makes training any machine learning model on this representation infeasible. The second problem is equally limiting. One hot encoding does not place similar entities closer to one another in vector space. If we measure similarity between vectors using some kind of distance, the similarity is 0 for every comparison between entities. So we can greatly improve embeddings by learning them using a neural network on a supervised task. The embeddings from the parameters, weights of the network, which are adjusted to minimize loss on the task. The resulting embedding vectors are representation of categories where similar categories are closer to one another. For example, if we have a vocabulary of 50,000 words used in some collection like movie reviews or something more, we could learn only 100 dimensional embeddings for each word using an embedding neural network. Words in the vocabulary that are associated with positive reviews, such as brilliant or excellent, will come out closer in the embedding space because the network has learned these are both associated with positive reviews. Or, for example, books that link to similar Wikipedia pages, yes, they are similar to each other. So the resulting embeddings should position similar books closer to each other in the vector space. figuring out how to create a control task to find relevant views is the hardest part of creating an embedding. And it is configured and executed specially for each task. Okay, let's see an abstract scheme of how does vector database work. We've got embeddings vector, put them into database. Vector database has a lot of data, but how can we search information? How should we store data to quick access? How does query execute? And there we have problems. First is vague search criteria. Structured data queries are precise Boolean predicates, but vector queries rely on a vague notion of semantic similarity that is hard to accurately capture. Large size. A structured query usually only accesses a small number of attributes, make it possible to design read-efficient storage structures, such as column stores, but vector search requires full feature vectors. Vectors sometimes even span multiple data pages, making disk retrievals more expensive while also straining memory. Expensive comparisons. Attribute predicates, for example, less, more, or equal, can mostly be evaluated in very fast time, but a similarity comparison typically requires much more time depending on dimensionality. Lack of structure. Structure's attributes are mainly sortable or ordinal, leading to partitioning ranges or categories that can be used to design search indexes. But vectors have no obvious sort order. They are not ordinal, making it hard to design indexes that are both accurate and efficient. Incompatibility with attributes. And structured queries over multiplied attribute indexes can use simple set operations, such as union or intersection, to collect results into final result set. But vector indexes typically stop after finding several most similar vectors. And combining these with the result from the attribute index scan can lead to fewer than expected results. On the other hand, modifying the index scan operator to account for attribute predicates can degrade index performance. It remains unclear how to support hybrid queries over both attributes and vectors in the way that both efficient and accurate. Overcoming these obstacles has led to new approaches to query processing, storage, and indexing, and query optimization and execution. Query processing in vector databases begins with a search specification consisting of the similarity score and the query type. Search criteria are conveyed to the system through a query interface. Once a query is received by the system, it's processed by executing a chain of operators over the vector collection. So first, we have to understand distance between vectors, and there we can use such popular similar score like Euclidean distance or cosine similarity. There are most popular similar score, but to achieve different goals can be used another distance such as Minkowski, Mahalanobis, Hamming, and so on. So there is Euclidean distance, and this is cosine similarity. And well, we know the distance between vectors, but how does query work? Most vector databases support nearest neighbor queries. where the aim is to retrieve vectors from dataset that are physical neighbors of search query in vector space. These queries may aim to return exact or approximate nearest neighbors, and may also specify the number of neighbors to return. It can be called as CK search query, where C indicates the approximation degree, the radius, and K is the number of neighbors. Out of these, most vector databases support the approximate K nearest neighbors, or ANN query, which returns K vectors from dataset that are within a radius centered over search query. And C times the distance between Q and its closest neighbors. Exact K nearest neighbors search can be prohibitively expensive for large data sets. Thus, real-world vector search systems adopt approximate nearest neighbors, search that can achieve much higher system performance. Many scores have been proposed over the years, but how to select an appropriate score for a particular application remains unclear. Ideally, a score is selected so that query answers accurately reflect the true semantic similarities between real-world entities representation by the vectors. But so far, there are no principles guiding score selection, and as a result, score selection tends to be based more on informal rules distilled from experience rather than on theory. Many vector databases offer this as a choice to the user, and how to support automatic score selection remains as an open problem. And there's one more problem. When dimension grows and when the dimensions are independent and identically distributed, the Euclidean distance between the two farthest and the two nearest vectors approach equality as a variant nearest zero. The effect of this curse of dimensionality is that vectors become indivisible. Attempts to avoiding the curse have led to using other distances, such as Minkowski distance, Manhattan, Chebyshev, is an effort to recover discernibility. While all search and range queries can be answered by comparing search query with each of the numbers of vectors, the complexity of this brute force approach is very large, because very large dimensional and number of vectors. Instead, vector indexes speed up queries by minimizing the number of comparisons. This is achieved by partitioning a dataset so that only a small subset is compared, and then arranging the partitions into data structures that can be easily traversed. Unlike typical attributes, vectors are not obviously sortable. They cannot be easily categorized. To achieve high accuracy, these indexes rely on novel techniques which can be referred to as randomization, learned partitioning, and navigable partitioning. The large physical size of vectors also leads to use of compression, namely a technique called quantization, as well as disk resistance designs. Partitional techniques, randomization aims to exploit probability amplification of multiplied independent events, allowing indexes to better discriminate truly similar vectors from dissimilar ones. Learning-based techniques aim to uncover an internal structure of dataset so that it can be partitioned along this structure. These techniques can be supervised or unsupervised. And navigable partition. Instead of fixating on absolute partitions, navigable indexes are designed so that different regions of dataset can be easily traversed. Some partitioning stages are data independent, where the rules are the same for any data distribution, but the majority are data dependent. If updates to dataset alter its distribution, then indexes based on that dependent stages may eventually become unbalanced over time. In many cases, this can only be resolved by rebuilding the index. Storage techniques, very interesting quantization. A quantizer maps a vector onto a more space-efficient representation. Quantization is usually lossy, and the aim is to minimize information loss while simultaneously minimizing storage costs. And disk-resistant designs compared to memory-resistant indexes, which only minimize the number of comparisons. Disk resistance index additionally aim to minimize the number of retrievals. And there are three basic types of indexes using in vector databases. Tables divide data into buckets containing similar vectors. Trees are a nesting of tables. Graphs connect similar vectors with virtual edges that can be then traversed. All of these structures are capable of achieving high query accuracy, but with different constructions, storage, and maintains characteristics. And let's take a look at table indexes. The main consideration for table-based indexes is the design of the bucketing hash function. The most popular table-based indexes for vector databases tend to use randomization and learned partitions as shown as table. For randomization, techniques based on locally sensitive hashing are popular due to robust error bounds. For learned partitions, learning to hash directly learns the hash function, and indexes based on quantization typically uses k-means to learn geometric clusters of similar vectors. All of these indexes have similar construction and search characteristics. For construction, each vector is hashed into one of the buckets. The total complexity is typically not very much. For LSH, each vector is hashed multiplied times. For quantization-based approaches, k-means multiplies the complexity by a constant factor. For search query is hashed onto a k, and then the corresponding bucket is scanned. One of the main criticisms of LSH is that the storage cost can be large due to use of multiplied hash tables. For in-memory vector databases, large memory requirements can be impractical. While some efforts aim to reducing the storage costs, other efforts have target vector compression using quantization. Many of these techniques use k-means centroid as the hash k. Quantization-based indexes is flat index, support a number of flat indexes where each vector is directly mapped into its compression version without any bucketing. The standard quantizer index, SQ, performs a bit-level compression, for instance, by mapping 64-bit doubles into 32-bit floats. The PQ index directly maps each vector onto its PQ code. Next index, inverted file index with SQ. The vectors are compressed using SQ and bucketed to their nearest centroid. And the next one, first buckets vector using k-means over a small number of centroids, and then trains a PQ quantizer by sampling a few vectors from each of the bucket. For tree-based indexes, the main consideration is the design of the splitting strategy used to recursively split datasets into a search tree. A natural approach is to split based on distance. The main techniques include pivot-based trees, such as VP tree, MEM tree, k-means tree, and trees based on deep learning. But while these trees are effective for low dimension, they suffer from curse of dimensionality when applied to higher dimensions. High-D tree-based indexes tend to rely on randomization for performing node splits. On picture is shown KD tree. This is a popular tree. The point space is divided on regions. Planes perpendicular to the coordinate axis are drawn so that there are approximately 50% of points in each area. The division stops if there are 2-3 points in each area. For example, Y divides first origin space in half points, and the next one, X, divides the upper area in half, and the latest divide this one. And the division into regions is described as a graph. The area is determined by the coordinates of the query, and a search is performed for neighbor closest to Q. The sphere is constructed, and its intersections with the planes, Y and X, are determined, and the graph is navigated left or right, and a comparison is performed between distance this and searching distance for points in these regions. Random trees, the point space is also divided in regions, but the directions of the planes are random. When dividing, the number of points in the area is also random variable, but in some range. The division into regions is described as a graph, but for directions. And for the query, the graph navigation determines the area to which search inquiry belongs. In the area, search is performed for nearest neighbors of Q, and only in this area. There is no need to build spheres and navigate the graph by comparing the distance between points. Graph-based index is constructed by overlaying a graph on top of the vectors in space, so that each node is positioned over the vector within the space. This includes distance over the nodes, which are then used to guide vector search along the edges. The example is shown in this figure. The main consideration for these indexes is edge selection. In other words, deciding which edges should be included during graph construction. Graph-based indexes encapsulated all the partitioning techniques. Many graphs rely on random initialization or random sampling during construction. the k nearest neighbor graph associated each vector with its k nearest neighbors. Other graphs, including monotonic searching networks and small word graphs, aim to be highly navigable, but differ in their construction. Graph-based search techniques have been shown to perform well in practice. There's hierarchical navigable small worlds. 2 nodes are randomly assigned to the top layer, 2 to the middle layer, and 3 to the bottom layer. The hour degrees in each layer are bounded by k to modulate search complexity. Vertical edges allow the search algorithm to traverse down the layers, while horizontal edges allow traversal within a layer. If the workload is write-heavy, then table-based indexes may be preferred, as they generally can be efficiently updated. For read-heavy workloads, tree or graph indexes may be preferred, as they generally offer logarithmic search complexity. Aside from these indexes, there have also been efforts at mixing structure in order to achieve better search performance. For example, navigating graph and tree NGT index uses a tree to initially partition the vectors and then use a graph index over each of the lead nodes. But when we talk about query, we have to talk about query optimization, and there may be multiple ways to execute a given query. The goal of the query optimizer is to select the optimal plan, typically the latency minimizing plan. To achieve this goal, the first step is plan enumeration, followed by plan selection, and then query execution. As vector search queries tend to consist of a small number of operators, in many cases, predefining the plans is not only feasible, but also efficient, as it saves overhead of enumerating the plans online. But for systems that aim to support more complex queries, the plans cannot be predetermined. For extended vector databases on relational systems, a relational algebra can be used to express these queries, allowing automatic enumeration. To identify the optimal query plan, existing vector databases perform plan selection either by using handcrafted rules or by using a cost model. Vector operators can take advantage of hardware accelerator in order to reduce query latency. Vector databases can also use distributed search to reduce the computing burden for a single machine. And to increase throughput, multiplied searches can be conducted in parallel over the distributed cluster. For write-heavy workloads, vector databases can sacrifice consistency for write throughput by using out-of-place updates, which allow index updates to be deferred until more suitable times. Distributed search, I'd like to discuss later, so I missed this slide. And let's talk about challenges and open problems. First is the similarity score selection. The semantic quantity of different similarity scores is still challenging to understand, and there is no rigorous guidance on how to select which score for which scenarios. Operator design, designing efficient and effective hybrid operators remains challenging. For graph indexes, block first scan can lead to disconnected components that either need to be repaired or that require a new search algorithms for handling this situation. Existing offline blocking techniques are limited to small number of attributes categories. For visit first scan, estimating the cost of the scan is challenging due to unpredictable backtracking, complicated plan selection. Incremental search. Some applications, such as e-commerce and recommender platforms, make use of incremental KNN search, where K is efficiently very large, but its retrieval in small increments so that results appear to the seamlessly delivered to the user. While technique exists for this type of search, it's unclear how to support the search inside vector indexes. Multi-vector search is also important for certain applications such as face recognition. Existing techniques tends to use aggregate scores, but this can be inefficient and it multiplies the amount of distance calculations. Generic multi-attribute top key techniques also are hard to adapt to vector indexes. Security and privacy. As vector search becomes increasingly mission critical, data security and user privacy become more important, especially for vector databases that offer managed cloud services. There is a need for new techniques that can support private and secure high-dimensional vector search. There are a lot of vector databases. There are not all vector databases, and the variety of data management techniques has led to an equal diverse landscape of commercial vector databases. They can be broadly categorized as native systems, which are designed specially for vector data management, and extended systems that add vector capabilities on top of an existing system. Native systems are characterized by small query APIs, simple processing flows composed of a low number of components, and basic storage model, making them highly specialized as a vector data management. This system can be further divided into two subcategories. Those are targeted mostly vector workloads, where the majority of queries access the vector collections, and those that target mostly mixed workloads, where queries are also expected to access non-vector collections. Mostly mixed workloads may consist of traditional attribute queries or textual keyword queries, along with typical predicates and non-predicate vector queries. Let's see, it's VELT. VELT is the serverless vector database aimed at providing scalable non-predicated vector search instead of a single centralized system. VELT spans a Kubernetes cluster consisting of multiplied agents. The vector collections is sharded and replicated across the agents to increase throughput and decrease latency via skate together. An individual VELT agent contains an NGT graph index built over its local shard. VELT also supports out-of-place updates on each local replica using a simple update queue. Veld is designed based on the microservice architecture. Veld components are highly decoupled into small components and connected, which increases the overall agility and maintainability of Veld. All components in Veld are containerized, which means you can easily deploy Veld components in any environment. All components support cloud-native based observability features. All the vector data and indexes are distributed to Veld agents in the Veld cluster. Whenever you search vector in cluster, all agents can process parallelly and merge the result by gateway. Veld can integrate with Kubernetes. Kubernetes supports container orchestration. All components in Veld can be managed by Kubernetes automatically. So Veld agent is the core component of Veld, the approximate nearest neighbor search engine, and stores the graph tree construction on memory for indexing the vectors. Veld agent uses NGT graph as a core library. Gateway has to load a balance the user request and forward user request to the Veld agent based on the resource usage of Veld agent and corresponding cluster node. In addition, it summarizes the search result from each agent and return the final search to the client. And Discoverer provides agent discovery service to discover active agent pods in the Kubernetes cluster. It also retrieves the corresponding valid agent resource usage, including pod and node resource usage for gateway to determine the priority of which Veld agent handles the user request. And the manager controls the timing of the indexing of the agent. Since the search operation will not work during the agent index operation is running, thanks to controlling the timing of indexing by manager, index operation of Veld agent can be triggered and controlled by manager intelligently. It retrieves the active agent pods from the discoverer and triggers the indexing action on each Veld agent. Pinecone is very popular native cloud database. It offers a scalable distributed system similar to Veld, but as it offered as a managed cloud-based service, it can be a more user-friendly option. Pinecone serverless runs as a managed service on different cloud platforms. Client requests to go through an API gateway to either a global control plane or a regional data plane. All vector data is written to highly efficient distributed object storage. And there are mostly mixed systems. They aim to support more sophisticated queries compared to mostly vector systems. In general, they support a greater variety of basic queries, including more support for exact and range queries, in addition to more query variants. These systems likewise have no need to query writers or parsers, but some, such as Milvus or Manu, Zilis, make use of query optimization. Milvus is aimed at comprehensive support for vector search query, and Manu adds additional features on top of Milvus. All three basic query types are supported, in addition to the three query variants. Multiply search indexes are also supported, and predicated queries are handled by cost-based optimizer. On picture, we can see Manu architecture. There are 4 layers. Access layer consists of stateless proxies that serve user endpoints. They work in parallel to receive requests from clients, distribute the request to the corresponding processing components, and aggregate partial search results before returning to clients. Coordinator layer manages system status, maintains metadata of the collections, and coordinates the system components for processing tasks. There are 4 coordinators, each responsible for different tasks. And the worker layer conducts the actual computation tasks. The worker nodes are stateless. They fetch read-only copies of data to conduct tasks and don't need to coordinate with each other. This ensures that computation-intensive worker nodes can be easily scaled on a demand. And the storage layer persists system status, metadata, the collections, and associated indexes. Manu uses etcd, a key-value store, to host system status and metadata for the coordinators. This provides high availability with its ladder election mechanism to failure recovery. When metadata is updated, the updated data is first written to etcd and then synchronized to coordinators. It's interesting that the high latency that comes with the object storage is not a performance bottleneck, as the worker nodes conduct computation tasks on in-memory, read-only copies of data. Extended systems inherit all the capabilities of an underlying data management systems and are necessary, more complex compared to native systems. But these systems are also more capable. Nearly all the extended systems support all 3 basic queries types and multiplied indexes, and all of them support query optimization. These systems likewise divide into 2 subcategories, those where the underlying system is NoSQL and those where is relational. Many of the hallmarks of NoSQL systems, such as seamless storage, distributed architecture, and eventual consistency, are present in native systems, making a NoSQL extended vector database much like a native systems. And there are a lot of examples of NoSQL system. Vespa is scalable distributed NoSQL system designed for large-scale data processing workloads. Vespa aims at more general data processing tasks, hence it is equipped with a flexible SQL-like query language. Cassandra is a popular distributed NoSQL system. Vector search capability, I think it's already have. They interheading index into the storage layer, implementing scale together across replicants, and extending the Cassandra query language with vector search operators. Databricks, the Spark-based Databricks platform is expected to support vector search including predicated queries, and so on. Aside from Vespa, several other document-based NoSQL databases have now been extended to support vector search. And vector search capability has also been extended to NoSQL systems or other than document stores. And for extended relational systems, their features mostly come from the inherent capabilities of relational systems. For example, SQL already is sufficient for expressing search queries, and these queries can already be answered by most relational engines upon adding a user-defined similarity function. But this is perhaps by single store, which offers exact KNN and range search through its native relational engine without any vector search indexes. Subsequently, extended relational systems focus more on tightly integrating vector search capability alongside existing components. Single store is a cloud-native hybrid transactional and analytical database based on the distributed row store for fast writes alongside column stores replicants for fast reads. Vector search is handled by the native relational engine, extended with functions for calculating. PACE extends Postgres SQL, which is flat quantization index, and small world index in order to support vector search. And PG vector, its extension for PostgreSQL, brings a vector data type, functions over this data type, and flat and other indexes access methods into PostgreSQL. Vector queries are issued using SQL. Otherwise, exact brute force scan is used. Plan selection is performed by existing PostgreSQL query optimizer. And other features such as replication, fault tolerance, access controls, and so on are provided by PostgreSQL. There also have AnalyticDB, ClickHouse, and MyScale. It's a column database aimed as fast analytical with asynchronous mechanisms for fast ingestion. It supports vector queries, and likewise, MyScale is a cloud service using ClickHouse as the backend. And priority search index called multi-scale tree graph, which is shown to outperform both very popular indexes. And when we talk about databases, we have to talk about scalability. Generally, database scalability refers to the dynamic capacity to expand or contract system resources like CPU, storage, and memory to seamlessly align with evolving business demands. There are two fundamental types of scalability: vertical and horizontal scalability. Vertical scalability involves increasing the capacity of a single database server by adding resources such as CPU, memory, storage, and its limitations. While it provides a quick and direct solution, it's important to note that there is an upper limit to how much a single server can scale before it hits hardware consistency. Understanding this limitation is key to making effective scalability decisions for real-world scenarios. And horizontal scalability involves adding additional service to distribute workloads, offer significant benefits. This strategy partitions large datasets and distributed them across all these nodes. By gradually adding nodes to the database cluster, horizontal scalability opens up a possibility of virtually limitless expansion. It also enhances fault tolerance, as the system can seamlessly redistribute tasks among remaining nodes in the event of a node failure. And the sharding is a database design principle in which data is split into parts and placed on different shards. Sharding is used if the system requires more and more resources, but the vertical scaling out of cluster cannot be used due to physical limitations. To distribute data across multiple servers and ensure their security and integrity, you need a database with appropriate architecture, a shared database. And sometimes the concept of sharding is confused with replication and partitioning, but in fact, these are different areas of scaling that can be implemented with a single database. Sharding works on the shard nothing architecture, where a single node in a computer cluster processes user requests independently. When the user tries to access the database, only the shard containing the user's information will become active and process the incoming request. There are a lot of sharding methods. Range-based sharding or dynamic sharding splits a database into shards based on a specific value range. Developers divide the data into logical shards using a shard key. They can select the key based on a column that organized data into groups or create new one. It's very simple to do, but you can easily get an uneven distribution of data and load. If the key is some kind of counter that is only growing, then all new data will fall on the last shard and it will be suffocate. If it's necessary it's necessary to choose the key very carefully and monitor how everything is distributed. Key-based sharding is also known as hash-based sharding, food of the hash function. A shard keys act like a primary key or a unique identifier for individual rows. Queries over a range of keys become extremely inefficient as they require accessing of the shards. The choice of hash function is important. It should give a good distribution. Adding new shards may require hashing and moving almost all the data. And this is a problem. Vertical sharding splits the entire column from the table and put those columns into new distinct tables. Data is totally independent. Also, each partition holds both distinct rows and columns, so we can split different features of an entity in different shards on different machines. Certain shards may become hotspots if they contain highly accessed columns, leading to uneven distribution of workloads. Making changes to such schema, such as adding or removing columns, may be more challenging in the vectorally sharded systems. Changes can impact multiplied shards and require careful coordination. And directly based sharding, a certain key value corresponds to a certain shard where the necessary data lies. The application first goes into the directory, finds out where to knock, and then goes to the data. The directory itself becomes a potential bottleneck and point of failure. It needs to be made highly accessible and scalable. Each data request requires additional access to the catalog with increases latency. And unlike traditional databases that use simple key-based sharding, vector databases often employ specialized strategies. For example, some systems use clustering algorithms like k-means to group similar vectors into the same shard, improving search efficiently by reducing the number of shards required for a similarity lookup. Each shard is managed by a node, and a coordinator service routes queries to relevant shards. For instance, when a user searches for a vector similar to a query embeddings, the database might broadcast the request to all shards in parallel and then aggregate results. However, sharding introduces challenges like uneven data distribution. To address this, system may dynamically rebalance shards or use hybrid approaches. At the moment when the vector database is divided into several shards, every part of the application interacting with the data must be changed or completely rewritten, which entails significant developer costs. Developing an effective partitioning strategy becomes a crucial factor, as well as implementing routing logic to ensure that data is routed to the desired shard. Managing atomic transactions across multiplied shards often requires application restructuring to avoid cross-shard operations. In addition, failure scenarios must be handled gracefully to prevent operational failures when some shards become unavailable. And sharding vector database problems, data distribution imbalance, hotspots in multi-user systems. Data distribution can range from hundreds to billion of vector per tenant, and this imbalance creates hotspots when some shards are overloaded and other are idle. Resharding, choosing the right number of shards is almost impossible. Too small an amount leads to frequent and expensive resharding operations. Too much creates unnecessary overhead metadata, increasing complexity and reducing performance. Complexity of schema modification. Many vector databases implement sharding by managing multiplied underlying databases. This makes synchronizing schema changes between shards an error prone, which slows down development cycles. Inefficient use of resources. In databases related to storage and computing, it's necessary to carefully allocate resources among all nodes. Usually, when resource usage research 60 or 70%, it's necessary to start planning reallocation. So it's better to use DB tools. Some databases, MongoDB, Elasticsearch, ClickHouse, Milvus, Pinecone, and other are able to distribute data between their instance, and it's enough to do best configuration. And this is best option. Of course, when we talk about elasticity of vector databases, we have to talk about elasticity of cloud. Elasticity of cloud meets the requirements of vector databases, which often have to cope with the changing workloads and rapidly growing amounts of data. The cloud's ability to dynamically allocate resources ensures efficient scaling without the need to significant initial investments in physical infrastructure. Migrating a vector database to the cloud offers several advantages, especially as organizations scale their artificial intelligence, machine learning, and data-driven applications. Here are some key reasons why such a migration is beneficial. Scalability. The cloud platforms allow seamless scaling of compute and storage resources to accommodate growing vector data. Performance optimization. Cloud provides optimized vector database with built-in indexing for fast similarity searches. Cloud performance provide on-demand GPU to speed up vector operations. Cost efficiency. Avoid upfront hardware cost and pay only for used resources. Global accessibility and low latency. Serve global users with low latency access by developing vectors database closer to end users. Easily connect to other cloud services for end-to-end workloads. High availability and reliability. Cloud provides offer replication, failover, and disaster recovery options to ensure uptime. Simplified data protection with scheduled backups and point-in-time recovery. Security and compliance. Benefit from cloud-native encryption, control, and compliance certifications. Use private networks to secure sensitive vector data. And simplified integration with machine learning. Cloud vector databases often integrate with machine learning service for streamlined development and support for streaming data to keep vectors synced with the changing data. Collaboration and DevOps. Enable distributed teams to collaborate on vector data without infrastructure constraints. So migrating to the cloud is ideal for organization needing scalability, performance, and ease of management for vector data. However, evaluate trade-offs based on your specific user case. Migration vector base to the cloud requires careful planning to ensure data integration, performance, and cost efficiency. And I asked DeepSeek how to migrate a vector database to cloud. And it told me next steps. First, access your current setup. Document the size of your vector database, identify dependencies, pick load times and scalability needs, and so on. The next step, plan the migration strategy. Move data to a cloud, gradually shift workloads while keeping some data on-prem, use cloud provider tools and others. Step 3, prepare the cloud environments. Configure roles for least privileged access. Create network with security groups to restrict access. For managed service, follow provider docs. Optimize performance, configure indexes, and other. Step 4, migrate data, export them, dump existing vectors for format like JSON, use database-specific tools, and transfer to cloud. Import data. Step 5, test and validate. Check metadata integrity, compare latency throughput against SLA, optimize indexes or scaling if needed, application integration, update connection strings, test end-to-end workflows. And step 6, cut over and monitor, go live, redirect traffic to the cloud database, have to do post-migration checks, set up cloud monitoring, optimize costs, and so on. And step 7, maintain the iterate, backups, updates, scale, and validation, and other. But there are many issues how to migrate exactly vector database to cloud. Their vector database requires reindexing post-migration to maintain query performance, while traditional database can often reuse existing indexes. Vector databases need performance validation for ANN queries, while traditional databases focus on traditional integrity. Vector databases often lack standardized migration tools, but requiring custom pipelines. Cloud vector databases may need GPU instances, increasing cost complexity. Vector databases require machine learning centric validation, can be more expensive to operate at scale due to compute needs. Migrating the vector databases often requires downstreams updates to machine learning models using embeddings. So it's better to deploy databases, vector databases directly in the cloud. There are a lot of cloud native vector databases: Pinecone, Milvus, Zilis, Manu is the same, Zilis, Chroma, White, and others. PG vector also can deploy in the cloud. So it's better to deploy database directly in cloud. And when we talk about clouds, we have to keep in mind SDN. OpenSDN, software-defined networking, refers to an open source approach to software-defined networking, which decouples the network control plane from the data plane, enabling centralized programmable network management. And OpenSDN and cloud computing are highly complementary, enabling agile, capable, and cost-efficient network management in modern cloud environments. So using OpenSDN and cloud, you can get agile, cost-efficient, future-proof networking. If you want full control over cloud networking, multi-cloud consistency, or such innovation, OpenSDN is what you need. But vector databases and OpenSDN serve different primary purposes. Combining them enable, but they can serve, while vector databases and OpenSDN serve different primary purposes. Combining them enables artificial intelligent augment networking, where vector similarity drives dynamic intelligence network control. This is cutting edge, but still experimental. Most production SDN systems today don't yet leverage vector database heavily, but I think it's our future. But OpenSDN is the main theme of this conference, so other guys can talk deeply about this. Thank you, and if you have any questions, please.
Thank you, Olga.
Thank you.
Any questions?
It's very hard. It's a new theme, vector databases. It's very interesting, but it's a very deep theme. And yes, it's very hard to understand.
At least you introduce some kind of a leading edge of database that should work well with the OpenSDN. So I think it's great to understand it. Okay.
Yes, I agree.
Okay. I think we all have to digest a little bit more, and today we really okay. Hold on. Okay, there's one question from the people online. Hold on one second, Olga. What question? Can you put it on? Okay, it's on the chat. Let me see. 1 second.
Can you please repeat the main stages of data storing and retrieving in the vector database? It's a slide number.
Repeat the main stage.
The
Okay.
main
Yes. Can you please repeat the main stage of data storing and retrieving of vector database? Okay.
Of data storing and retrieving and vector databases. It's of data storing. The main stages is to use very huge, very large images, very huge information in vector databases. But it's right that data vector bases can be used to compress the amount of stored data. Yes, this is right. When you use vector databases, you can embedding information into small size vectors, much more less than your information, and put them into vector databases. But it allow you to fast query, fast search information, and it's better to use for large objects.
Okay.
And about which SDN uses vector database, no one. It's imagine it's proposed for combine OpenSDN and vector databases. No one SDN is using vector databases, but for example, you can use vector database to real-time queries, compare incoming traffic against known anomalies, or user intents are converted into vectors using models, and vector database retrieves the host machine network policies, and OpenSDN applies the matched policies programming APIs. So you can use dynamic load balancing with reinforcement learning. So historical network states are embedded as vectors, and reinforcement learning agent requires the vector database for similar past states to predict optimal paths. And OpenSDN enforces the reinforcement learning agents' decisions, and so on.
Okay. Olga, I would say this vector database is an open source, right? That if you can.
Some are open source and some are not open source. There are a lot of
what's the brand of commercial vector database?
It's our future because the huge information we have to store, and we have to fast find information, and the vector database is one of the decision, and many relational databases added extensions due to vector is our future.
Okay, I see. Okay, any other questions? Hold on 1 second, Olga. There might be one more from all. 1 second, Olga. There we saw one. Okay. Olga, there's a question. I will read it out to you, okay? There are some, the question is, there are some specific method on migrate different type of vector database. For example, PG vector, chroma, Pino, and this person, he said, I use Olama model to embed. Okay, that's the end of the question. You want me to repeat?
Yes, please.
Okay.
I understood that there are a lot of vector databases, and you use indexes or something else.
You asked that person?
Repeat it again.
Okay, I'll repeat again. There are some specific method on migrate different type and different type of vector database. For example, the method that used for migrate the database, like PG vector, chroma, Pino. But this I use Olama model to embed. Okay, so I didn't see any question mark in this one. So what's your opinion on that one? Migrating different type.
It's okay. In my opinion, you have a right way, because PG vector is very interesting extension for a PostgreSQL database, but it's not very good for sharding. Better use sharded database like Melvas, Pinecone, and so on. But if you can use any machine learning, any large language learning model to learn your vector database to get embeddings. But if you use this model, you have to use this model to find queries. So if you learn, if you get embeddings, somehow get embeddings, please check, is it right to get queries? Is it okay when you get queries? Is it that you need? But there's no robust to use which machine learning model you have to choose.
Okay. The person who asked this question is Mr. Sawangpong Muatpet. He's also very keen on the using AI, machine learning, and also he's going to be our instructor on Linux, Essential Linux Foundation, a lot of courses. So that's just his background. Okay, no more question, right? Okay. Thank you very much. Give a big applause for Olga.
Thank you very much. Thank you for inviting me. I'm very glad to be part of this great conversation. Thank you very much.
Thank you, Olga. Thanks for your time, and hope that you can come back and give us more knowledge like today. Thank you.
Yes, there is a very huge theme, very interesting. Thank you very much. Thank you very much for listening.
Thank you. All right. Have a good day. All right.
Thank you. Bye.
Bye.